To understand binary numbers, I believe that we need to look a little bit closer at our decimal system. Now, decimal starts with deci. We know that represents 10. So our decimal system is base 10. We have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that is 10 options 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 options to represent the numbers that we understand. Using those 10 options, then, we put them into columns which represent multiples of 10. So if we think about our ones column, and then we have a tens column, a hundreds, and a thousands, 10,000s, 100,000s, 1,000,000, so on and so on and so on, we can look at it another way as 10 to the 0 power, 10 to the first, 10 to the second, 10 to the third, and so on. So our base 10 system uses tens to represent each column and has 10 choices to put into those columns. So when we write the number 1,342, we are saying that there are 2 ones. We are saying that there are 4 tens. We're saying that there are 3 100s. And we are saying then that there's 1 1,000s. And if we add those together, we get 1342. It all works out. Same concept is going to apply to the idea of binary. So binary has bi as its prefix. Bicycle has 2 wheels. Binary has 2 choices. We are a base 2 number when we are using binary. And our 2 choices are 0 and 1. That's all we get. And just like the tens create columns as we raise it to a power, binary uses 2's raised to a power to create columns. So we can have our, start over here, we can have our ones column, our twos column, our fours column, our eights column, 16s, 32s, 64s, 128s, and end at 256. That's as high as we're going to get for the concepts that we need for ultrasound. And so when we look at these columns, same idea, just as our tens, we are raising those to powers, we can figure out what our columns are representing by raising 2's to powers. So 2 to the 0 is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128, and 2 to the eighth is 256. So while you are studying binary and trying to keep it all straight, you have a couple options I believe that you can do. Memorize these numbers up on top here, or recognize that we are just starting from 0 to 8, raising 2's going along. If you have a calculator handy with you, then you can go through and do the math. However, I don't think memorizing the numbers are all that difficult. Knowing that you're starting with 1 doubled is 2, 2 doubled is 4, 4 doubled is 8, 8 doubled is 16, and so on. So we follow a nice pattern up on the top too of just doubling each number to represent each column as we go through. Now, just like with the tens, remember we had 1342. That said that we had the 1 1000s, 3 300s, 4 tens, 2 ones. We can use the same idea for binary, except remember, we only have these 2 choices to represent those columns. And so if we put a 1 in every single column, we are then saying that there's 1 256, 1 128, 1 64, 132, 116, 18, 14, 12, 11, all the way down. We are saying that all of these columns are active and that number is being represented. We could then translate that into the decimal number by adding all of these together. Erase a little bit more than I wanted to. And so let's just kind of jump in and let's try some examples here. I think that's probably going to be the best way to take a look at this. So when you are given a number in binary, we'll start Actually, yeah, we'll start with the binary number. So let's say we have the number 10011. All right, what number is this in decimal? Well, let's figure it out. So we need to list our columns that match up with 5 columns. So we need to have our 1s column, our 2s column, a 4s column, an 8s column, and a 16s column. We then are going to put in our numbers 1, 0, 0, 1, 1. If a 1 is present, we're going to write that number down. So we have 16, 2, and a 1. Simply add those numbers together. 16 plus 2 plus 1 equals 19. So 10011 is binary for the decimal number 19. Let's try another one. Let's make our binary number this number. All right, so we need a 1, 2, 3, 4, 5, 6, 7. We need 7 columns represented. So we need 1, 2, 4, 8, 16, 32, 64, and we can stop there. So let's go ahead and then write our numbers in. We have 1, 0, 0, 1, 1, 1, 0. Simply add any columns that have a 1 in it. So we would have 64, 8, 4, and a 2. We'll add those together and we get 12, 16, 18. We get 78. So 78 is how you would write this number in binary. Right? So pretty simple to memorize those columns, knowing that they make up our binary placeholders. Simply write your binary number underneath them, and then you know if there is a 1, you're going to add those numbers together. Now let's work the other way. Let's work with a decimal number. How do we translate that into binary? So let's pick a number. Let's do 45. How do we get 45 into binary? Now, the biggest number that you will need is the number, actually, how do I want to say this? Okay, so if we just write down all of our numbers, write down all of our columns, the biggest number that we're going to need is 32 to write a 45. So we don't need 256, 128, or 64 for this example. So the first thing we want to look at, how many 32, can a 32 go into a 45? The answer is yes. So we're going to put a 1 there. Now we have to figure out how much is left. So we're going to take 45 and subtract 32. And we will get, as a leftover, 13. Can 16 go into 13? The answer is no. So we're going to put a 0 there. We don't have enough space to make any 16s. We'll move to our next number. Can an 8 go into 13? The answer is yes. So we're going to put a 1 there. But then we need to subtract 8 from what we're working with. We'll go to the next column. Can a 4 fit in a 5? Again, the answer is yes. Subtracting that number, we're left with a 1. Can 2 go into 1? Nope. 1 can go into 1, so we are going to put a 1 there. So if the answer is yes, you put a 1. If the answer is no, you put a 0. So 45 in binary form is 101101. So you need to kind of keep a tally on the side. It's all very basic math, so you should be able to do this with paper and pencil. The more you practice it, the more it will become kind of like second nature, kind of just doing that math, figuring out how to put it all together. I'm going to leave our numbers along the top here. I think, like I said, memorize these numbers, maybe write it down on your cheat sheet. Just have these numbers in order for your test, for when you're working on your workbook, whatever you need to do to keep those numbers available to easily do the translation of binary numbers. So let's do another example. Let's figure out what binary number 129 is. So again, we're looking for the first number that completely fits into our decimal number, and that happens to be 128. So this one's kind of an easy one. We're going to say yes, 128 can fit in. So we're going to subtract 128 from 129. All we're left with is a 1. So we cannot fit any 64s into 1. 32 doesn't fit into 1. 16 can't go into 1. Nor can 8, 4, or 2. But 1 at the end does go into 1. So the number 129 in binary is 100000001. Okay. Well, let's just try another example. I'm going to just erase my numbers, and we'll do the number 87. Let's see what 87 is in binary. So we're looking down, 256 can't go in. And we could actually do this too, just as kind of a practice part of it. 256 can't, 128 can't, 64 can. So we're going to put a 1 in there. We then need to subtract 64 from 87, and we get 23. 32 cannot fit into 23, 16 can, so we'll put a 1, and then we need to subtract it. 7, that's all we have left. 8 cannot fit into 7, 4 can, so we'll subtract 4. We're left over with 3. 2 can fit into 3, so again, we'll put our 1 under the 2 column. 3 minus 2 is 1. 1 fits into 1. We don't need these leading zeros in binary. We can start with the first column. However, you do need this ending 0. If this 1 is not included, we need to include that 0 at the end. So if this was 86, then it would look like this. Including that last 0. Right? So just some things to kind of keep in mind. If it's an odd number, odds are always going to have this 1 in the ones place. If, say, it was 65, the answer would be 100000001. Remember, our answer for 129 was 100000001. 257 would be 100000001. So there are some patterns when we look at binary and how they kind of all work together. All right, let's do one more example, and I think that will probably be enough to understand the binary questions that are in your workbook. So let's do one more. Let's do 179. All right, so 256 cannot go into 179. 128, yes, that can go in there. So let's put a 1 there. That's a yes. We're going to take 179 minus 128. And our leftover is 11 and 1, 51. 64 cannot fit into 51. 32 can, so we'll put a yes and subtract 32. We get 19 left. 16 fits into 19, so we'll put a 1 there. Subtract 16, and we're left with 3. 0 does not fit into, or 8 does not fit into 3. 4 does not fit into 3. 2 does, and then we have an odd number, so we're going to put our 1 in at the end. So 179 in binary is 10110011. If you have any questions, I do highly encourage you to look on YouTube for other videos that explain how to do this. This, I think, is the easiest way to learn the basics of binary. This is how I learned it. This is how I figured out how to teach it. I wouldn't get super, super stuck on how to do binary. What we are really trying to get to, the core of knowing the binary part of this for physics, is that our scan converter works in zeros and ones. And when that information comes back from the transducer, let's say the transducer, transducer is going to get this analog information back, and demodulation will occur, and we'll kind of get this digital box that comes back. And let's say that gray that came back from that particular echo was given a number of 9. Well, then that gray 9 level, when it gets written into the scan converter, is going to be written as 1001. So the scan converter has to have at least 4 bits of memory to display those 16 levels of gray, but really the 9 level of gray. So the scan converter, again, will tell this pixel to be a 1, this pixel to be a 0, this part of the memory that goes with that pixel to be a 0, and then this last bit of memory that goes with that pixel to be a 1. And that's how that one pixel will be coded. It'll get a level, it'll be coded as a digital number. We have to have enough bits of memory to be able to code all those numbers in. Just again, as another example, let's say we had our demodulated number comes in and it got assigned a number of 256. So we need the 256 level of gray for that system. And to have 256, we have to have 8 bits of memory. So again, these are just, remember, our memory, our scan converter has all these pixels, and each pixel then is going to have 8 bits assigned to it. And so for 256, the first bit will get assigned a 1, because that's going to be a 1, and then the rest are all going to be zeros. So this pixel, for the 8 bits, will have a 1 assigned and then a 0 in the rest of the bits, and that will tell the digital scan converter to make that 1 pixel the 256th level. Let's say then this pixel below it comes back with a number of 132 is this next box that comes back. And so that number in binary, finish writing out the 256 there, that number in binary would be 100000100. So this first, so there's 1 pixel. This first bit of memory is going to have a 1 in it. The next ones are going to be 0. This one will get a 1, and then the last 2 will get 0. And so the 1 pixel that's associated with this layer of memory will get coded out so it can display the 132nd level of gray, whatever that is associated for that system. So again, binary just helps us to better understand how many levels of gray, how many shades of gray can a system display. Modern systems are usually 8-bit memories, so we can get at least 256 shades of gray. And just knowing that 1 pixel is only able to display 1 level of gray based on how the memory is coded with a digital number just helps us to understand a little bit more about how the scan converter works.